Static energy conversion of renewable technologies. Static energy conversion refers to the process of directly converting renewable energy sources into usable energy without the need for moving parts or mechanical components. This conversion is typically achieved through electronic and chemical processes. Here are some examples of static energy conversion in renewable technologies. A. Photovoltaic, PV, solar panels. PV solar panels convert sunlight directly into electricity using semiconducting materials. When sunlight strikes the solar cells, electrons are freed, creating an electric current. B. Wind turbines. While wind turbines have moving parts, the conversion of wind energy into electricity is considered static because the process involves direct generation without intermediate mechanical conversions. The rotating blades of the wind turbine transfer the kinetic energy of the wind to the generator, producing electricity. C. Hydroelectric power. In hydroelectric power plants, the potential energy of falling or flowing water is directly converted into electricity through turbines and generators. D. Solar thermal power. Some solar power plants use mirrors or lenses to focus sunlight onto a receiver, where the heat is used to generate steam and drive a turbine connected to an electricity generator. Static energy conversion technologies have the advantage of being relatively simple, reliable, and having lower maintenance requirements compared to dynamic systems. However, their efficiency may be limited by the characteristics of the energy source and the conversion process.
Dynamic energy conversion of renewable technologies. Dynamic energy conversion involves the use of mechanical components to capture, store, and convert renewable energy into usable forms. These systems rely on the movement of parts to achieve energy conversion. Here are some examples of dynamic energy conversion in renewable technologies. A. Ocean wave energy. Devices such as wave energy converters capture the kinetic energy of ocean waves and convert it into electricity. These devices often involve moving parts or hydraulic systems. B. Tidal energy. Tidal power plants use turbines or other mechanical systems to harness the energy from tidal currents and convert it into electricity. C. Geothermal power. In some geothermal power plants, steam or hot water is extracted from geothermal reservoirs underground and used to drive turbines connected to generators. Dynamic energy conversion systems have the potential to capture energy from more variable and intermittent renewable sources. However, they can be more complex, expensive to install and maintain, and may have higher environmental impact due to the need for mechanical infrastructure. In summary, both static and dynamic energy conversion play crucial roles in the utilization of renewable energy sources. The choice between static and dynamic approaches depends on factors such as the characteristics of the renewable resource, the location, efficiency, cost, and environmental considerations. Often, a combination of both static and dynamic energy conversion technologies is used in integrated renewable energy systems to optimize efficiency and reliability. Energy storage requirements. To mitigate intermittency issues, energy storage systems, e.g., batteries, are required to store excess energy and release it when renewable generation is low. Grid resilience. The grid stability and resilience can be impacted due to the variability of renewable energy, which requires careful planning and management. Addressing these challenges requires advanced grid management techniques, energy storage solutions, smart grid technologies, and supportive government policies to incentivize the transition to renewable energy while ensuring grid stability and power quality.
Distributed generation of renewable technologies. Distributed generation refers to the production of energy at or near the point of consumption, often on a small or medium scale. It involves deploying renewable energy sources in diverse locations throughout the grid. Common examples of distributed renewable technologies include A. Solar panels on rooftops, photovoltaic, PV, solar panels installed on residential, commercial, or industrial rooftops generate electricity for immediate use on site or can feed excess power back into the grid. B. Small wind turbines. Small-scale wind turbines can be installed on individual properties or in community wind projects to produce electricity locally. C. Micro hydropower. Small hydroelectric power systems can be implemented in rivers or streams to generate electricity for nearby communities. D. Biomass energy. Biomass power plants on a smaller scale can use organic waste to produce electricity for localized use. Advantages of distributed generation. Enhanced grid resilience. Distributed generation reduces the vulnerability of the grid to single points of failure and potential blackouts. Reduced transmission losses. Generating power closer to the point of consumption reduces energy losses during long-distance transmission. Increased energy independence. Local generation allows communities and businesses to rely less on centralized power plants and imported energy. Potential for off-grid applications. Distributed generation enables energy access in remote or rural areas without extensive grid infrastructure. Disadvantages of distributed generation. Higher installation costs. The upfront cost of installing many small-scale renewable systems can be higher per unit of capacity compared to larger centralized projects. Limited scaling potential. Distributed generation may not be suitable for meeting the energy demands of densely populated urban areas or industries with high power requirements. Grid integration challenges. Integrating multiple small-scale renewable systems into the existing grid infrastructure can be complex and require smart grid technologies. Distributed generation of renewable technologies. Distributed generation refers to the production of energy at or near the point of consumption, often on a small or medium scale. It involves deploying renewable energy sources in diverse locations throughout the grid. Common examples of distributed renewable technologies include A. Solar panels on rooftops, photovoltaic, PV, solar panels installed on residential, commercial, or industrial rooftops generate electricity for immediate use on site or can feed excess power back into the grid. B. Small wind turbines. Small-scale wind turbines can be installed on individual properties or in community wind projects to produce electricity locally. C. Micro hydropower. Small hydroelectric power systems can be implemented in rivers or streams to generate electricity for nearby communities. D. Biomass energy. Biomass power plants on a smaller scale can use organic waste to produce electricity for localized use. Advantages of distributed generation. Enhanced grid resilience. Distributed generation reduces the vulnerability of the grid to single points of failure and potential blackouts. Reduced transmission losses. Generating power closer to the point of consumption reduces energy losses during long-distance transmission. Increased energy independence. Local generation allows communities and businesses to rely less on centralized power plants and imported energy. Potential for off-grid applications. Distributed generation enables energy access in remote or rural areas without extensive grid infrastructure. Disadvantages of distributed generation. Higher installation costs. The upfront cost of installing many small-scale renewable systems can be higher per unit of capacity compared to larger centralized projects. Limited scaling potential. Distributed generation may not be suitable for meeting the energy demands of densely populated urban areas or industries with high power requirements. Grid integration challenges. Integrating multiple small-scale renewable systems into the existing grid infrastructure can be complex and require smart grid technologies. Resources evaluation and needs. Sizing of integration renewable systems. Evaluating resources and sizing integration for renewable energy systems is a crucial step in designing an effective and efficient renewable energy project. Here are some steps to consider. Resource evaluation. Solar energy. Assess the solar irradiance in the region where the solar panels will be installed. Tools like NASA's Surface Meteorology and Solar Energy Data Set, SSE, or online solar irradiance databases can provide valuable information. Wind energy. Measure wind speeds and directions at the proposed installation site. Historical wind data from local meteorological stations or online databases can be used to estimate the average wind resource. Hydropower. Evaluate the water flow rate and the head, vertical distance, available for hydropower installations. Stream flow data from relevant authorities or hydrological studies can be utilized. Biomass energy. Analyze the availability of biomass feedstocks such as agricultural residues, forestry waste, or organic waste generated by industries or households. Geothermal energy. Conduct geological surveys and exploratory drilling to assess the potential for geothermal resources in the area. Energy needs assessment. Analyze the energy demand in the target location. Consider current and future energy needs, including seasonal variations and trends. Identify the types of energy required, electricity, heating, cooling, and their respective load profiles, patterns of energy consumption over time. System sizing. Based on the resource evaluation and energy needs, size the renewable energy system to match the demand appropriately. Oversizing or undersizing the system can lead to inefficiencies and increased costs. For solar and wind energy systems, use the capacity factor, average actual power output over time divided by the maximum potential output, to determine the appropriate size. For hydropower, consider the flow rate and head to estimate the potential power generation capacity. Sizing for biomass and geothermal systems will depend on the availability and energy content of the feedstocks or resources. Integration and storage. Assess the need for energy storage solutions to address fluctuations in renewable energy generation. Battery storage, pumped hydro storage, or other energy storage technologies can help balance supply and demand.
Interfacing requirements of renewable systems. Interfacing renewable systems involves connecting renewable energy sources and related equipment to the electrical grid or other energy systems. The goal is to ensure efficient, safe, and reliable integration of renewable energy into the existing infrastructure. Here are some key interfacing requirements for renewable systems. Grid compatibility. Renewable energy systems must be compatible with the existing electrical grid to ensure smooth power flow and prevent disruptions. Grid codes and regulations dictate the technical specifications and performance criteria for connecting to the grid. The system must meet voltage, frequency, and power quality standards set by the grid operator. Power electronics and inverters. Most renewable energy sources, such as solar panels and wind turbines, generate direct current, DC, electricity. However, the grid operates on alternating current, AC. Power electronics, like inverters, are required to convert the DC power from renewables into AC power suitable for the grid. Synchronization and phase alignment. For grid-connected systems, the renewable energy sources must be synchronized with the grid's AC frequency and phase. This ensures that the power generated by renewable sources is in phase with the grid power, avoiding instability and blackouts. Grid protection and control. Renewable systems should have protective devices to isolate them from the grid during faults or disturbances. Additionally, they should have control capabilities to regulate the power output and response to grid requirements. Smart grid integration. Implementing smart grid technologies can enhance the integration of renewables. Smart grid features, such as advanced metering, demand response, and energy storage integration, can optimize the use of renewable energy and improve grid stability. Energy storage integration. Renewable energy sources are often intermittent, which means they don't provide a constant power output. Integrating energy storage systems, like batteries, can help store excess energy and release it during periods of low renewable generation, ensuring a steady power supply. Communication protocols. Renewable systems need to communicate with the grid operator and other components in the system. Standardized communication protocols, such as Modbus or IEC 61850, facilitate data exchange and system control. Safety and compliance. Interfacing requirements also encompass safety considerations.
Voltage control in smart grid. Voltage control is crucial for maintaining voltage levels within acceptable limits to ensure proper functioning of electrical equipment and prevent damage to the power system. In traditional power systems, voltage control is primarily achieved through automatic voltage regulators, AVRs, installed at substations. In regs, voltage control becomes more complex due to the decentralized and intermittent nature of renewable sources. Some methods for voltage control in regs are: A. Reactive power control. Regs can contribute to voltage control by adjusting reactive power output. Wind turbines and solar inverters can be equipped with control mechanisms to regulate reactive power flow. B. Volt bar control. Utilizing volt bar control strategies can help regulate voltage levels by adjusting the reactive power output of renewable sources based on the voltage measurements at various points in the grid. C. Coordinated control. Integrating voltage control algorithms with load frequency control and energy storage management can provide a more comprehensive and efficient control approach. D. Smart inverters. The use of smart inverters in solar PV systems can enable advanced voltage control capabilities by allowing real-time communication and control. To achieve effective load frequency and voltage control in power systems with a high penetration of renewable energy, a combination of these methods, along with advanced control and communication technologies, is often necessary. Proper planning, coordination, and integration of renewable energy sources are vital for maintaining the stability and reliability of the grid. Load frequency control, LFC. In regs, load frequency control becomes more challenging due to the intermittent nature of renewable sources. Solar and wind power generation depends on weather conditions, and their output fluctuates. Various methods are employed. A. Energy storage systems. Integrating energy storage systems like batteries can help store excess energy during high generation periods and supply it during low generation periods, stabilizing the grid frequency. B. Advanced control algorithms. Implementing advanced control algorithms that predict renewable energy availability and demand can enable more proactive load frequency control. C. Demand response. Implementing demand response mechanisms can incentivize consumers to adjust their electricity consumption during peak and off-peak periods, helping to balance the load. Nonlinear controllers. Nonlinear controllers are designed based on nonlinear control theory, which allows for more complex relationships between the input and output. These controllers are employed in systems with highly nonlinear behavior or when the operating range extends beyond the capabilities of linear controllers. Nonlinear controllers often use advanced control techniques, such as adaptive control, fuzzy logic control, or model predictive control, MPC. These techniques can handle more complex and dynamic systems and may provide better performance in certain scenarios. A. Fuzzy logic controller, FLC. Fuzzy logic controllers use linguistic variables to represent the system's behavior. Instead of using precise mathematical models, FLC relies on human-like reasoning to make control decisions based on fuzzy rules. It is particularly useful when dealing with uncertain or imprecise information. B. Model predictive control, MPC. MPC uses a dynamic model of the system to predict its behavior over a future time horizon. It then optimizes a control sequence to achieve desired objectives, such as maximizing energy production or minimizing costs. MPC is effective in handling constraints and disturbances in renewable energy systems. C. Adaptive control. Adaptive control techniques adjust controller parameters in real time based on the system's changing characteristics. This approach is suitable for systems with uncertain or time-varying dynamics. In renewable energy generation systems, nonlinear controllers are often employed in complex and dynamic components like grid-tied inverters or energy storage systems, where the behavior is nonlinear and requires sophisticated control strategies. In summary, both linear and nonlinear controllers play essential roles in renewable energy generation systems. Linear controllers are commonly used in simple systems with relatively predictable behavior, while nonlinear controllers are employed in more complex systems that require advanced control techniques to achieve optimal performance. The choice of controller depends on the specific characteristics and requirements of the renewable energy system being controlled.
Grid-connected and islanding operations. Grid-connected and islanding operations are concepts related to electrical power systems and the operation of distributed energy resources, DERs, like solar panels, wind turbines, and energy storage systems. Let's explore each term separately. Grid-connected operations. Grid-connected operations refer to the standard mode of operation for most power generation systems and consumers. In a grid-connected setup, power generation sources, such as power plants or renewable energy sources like solar and wind, are connected to an interconnected network of power transmission and distribution lines called the electrical grid. Consumers, such as homes, businesses, and industries, are also connected to this grid. Key characteristics of grid-connected operations. Bidirectional power flow. Power can flow in both directions, from the generation sources to the consumers and vice versa. Power plants supply electricity to the grid, and consumers draw electricity from the grid as per the demand. Stable frequency and voltage. In a well-maintained grid, the frequency and voltage levels are regulated within specific tolerances to ensure the reliable and efficient operation of electrical devices. Centralized control. Grid-connected power systems are centrally controlled and managed by grid operators who monitor and balance the electricity generation and demand to maintain grid stability. Interconnection of multiple sources. Various power generation sources can be interconnected, including fossil fuel power plants, hydroelectric plants, solar farms, wind farms, and more. Islanding operations. Island mode or islanded grid. Islanding operations, also known as island mode or an islanded grid, occur when a portion of the electrical system continues to operate in isolation from the main grid due to a grid disturbance or a fault in the main grid. This typically happens when there is a sudden loss of grid connectivity due to a fault, maintenance, or a natural disaster, and certain localized areas still have power generation sources available. Characteristics of islanding operations. Isolated power supply. The isolated portion of the electrical system operates as an independent microgrid, relying on local power generation sources and energy storage systems to meet the electricity demand within that area. Limited power resources. In islanding mode, the available power generation sources are limited to what is present within the isolated area.
Nonlinear controllers. Nonlinear controllers are designed based on nonlinear control theory, which allows for more complex relationships between the input and output. These controllers are employed in systems with highly nonlinear behavior or when the operating range extends beyond the capabilities of linear controllers. Nonlinear controllers often use advanced control techniques, such as adaptive control, fuzzy logic control, or model predictive control, MPC. These techniques can handle more complex and dynamic systems and may provide better performance in certain scenarios. A fuzzy logic controller, FLC. Fuzzy logic controllers use linguistic variables to represent the system's behavior. Instead of using precise mathematical models, FLC relies on human-like reasoning to make control decisions based on fuzzy rules. It is particularly useful when dealing with uncertain or imprecise information. B. Model predictive control, MPC. MPC uses a dynamic model of the system to predict its behavior over a future time horizon. It then optimizes a control sequence to achieve desired objectives, such as maximizing energy production or minimizing costs. MPC is effective in handling constraints and disturbances in renewable energy systems. C. Adaptive control. Adaptive control techniques adjust controller parameters in real time based on the system's changing characteristics. This approach is suitable for systems with uncertain or time-varying dynamics. In renewable energy generation systems, nonlinear controllers are often employed in complex and dynamic components like grid-tied inverters or energy storage systems, where the behavior is nonlinear and requires sophisticated control strategies. In summary, both linear and nonlinear controllers play essential roles in renewable energy generation systems. Linear controllers are commonly used in simple systems with relatively predictable behavior, while nonlinear controllers are employed in more complex systems that require advanced control techniques to achieve optimal performance. The choice of controller depends on the specific characteristics and requirements of the renewable energy system being controlled.
Filters for grid-connected system. In the context of a grid-connected system, filters play an essential role in ensuring the efficient and safe operation of the system. Grid-connected systems, like solar power systems or wind power systems, are designed to feed electricity into the utility grid. These systems generate electricity from renewable energy sources and synchronize their output with the utility grid's voltage and frequency. Here are some common types of filters used in grid-connected systems. Harmonic filters. Harmonics are undesirable voltage and current distortions that can occur in grid-connected systems due to nonlinear loads or power electronic converters. Harmonic filters are used to mitigate these harmonics and ensure the system's compliance with grid codes and standards. They can be passive, e.g., inductors and capacitors, or active, e.g., using power electronic devices to actively cancel out harmonics. ME, electromagnetic interference, filters. ME filters are used to suppress electromagnetic interference caused by the switching of power electronic devices in the grid-connected system. They prevent the system's high-frequency noise from affecting other sensitive electronic equipment on the grid or nearby. Power quality filters. Power quality filters are designed to address various power quality issues such as voltage sags, voltage swells, voltage flicker, and other disturbances. These filters help maintain stable and high-quality power output from the grid-connected system. Low-pass filters. In certain applications, a low-pass filter may be used to smooth out rapid voltage or current fluctuations and prevent high-frequency components from reaching the grid. High-pass filters. High-pass filters can be used to filter out low-frequency components in the system's output. They are used in specific cases where low-frequency content may need to be removed before the electricity is fed into the grid. Notch filters. Notch filters are used to attenuate specific frequencies or frequency ranges. They are employed when there are known frequency components or interference that need to be eliminated from the system's output. Anti-islanding filters. These filters are a critical safety feature for grid-connected systems. They detect islanding situations when the grid goes down, but the renewable system continues to generate power, and they disconnect the system from the grid to prevent feeding power into a potentially damaged grid.
Islanding detection methods. Islanding detection methods are techniques used in electrical power systems to identify and detect instances when distributed energy resources, DERs, such as solar photovoltaic systems or wind turbines, continue to generate power in an isolated manner during a grid outage. When a power outage occurs, the main grid shuts down to protect utility workers and equipment. However, if a DER system is still generating power during this time, it can create a potentially dangerous island of energy that could cause harm to workers attempting to repair the grid. Detecting the occurrence of islanding is crucial to ensure the safety and stability of the overall power system. Here are some common islanding detection methods. Frequency-based methods. These methods monitor the frequency of the electrical signal in the system. During normal grid-connected operation, the frequency remains relatively stable. However, when an islanding event occurs, the frequency may start to deviate from the standard value. Frequency-based methods include rate of change of frequency, ROCOF, and under/over frequency relays. Voltage-based methods. Similar to frequency-based methods, voltage-based methods monitor the voltage levels in the system. A significant change in voltage could indicate an islanding condition. Voltage-based methods include rate of change of voltage, ROCOF, and under/over voltage relays. Impedance-based methods. These methods analyze changes in the impedance characteristics of the power system. During an islanding event, the impedance may differ from the usual grid-connected values. Techniques like positive feedback impedance and reactive power voltage relays fall under this category. Rate of change of power, ROCP. This method measures the rate at which active power, real power, changes in the system. A rapid change in active power may indicate islanding. Frequency watt, FW, or voltage watt, VW, control. Some grid-tied inverters in solar photovoltaic systems utilize FW or VW control algorithms to detect islanding. These methods monitor the grid frequency or voltage and adjust the inverter's power output accordingly. If the grid parameters deviate beyond certain thresholds, the inverter may disconnect from the grid to prevent islanding. Communication-based methods. In certain cases, Communication between DERs and the Utility Control Center can be used to detect islanding. Applications of FACTS controllers are explained as follows. Voltage control and regulation. FACTS controllers such as static bar compensators, SBCs, and static synchronous compensators, STATCOMs, are used to regulate voltage levels in power systems. They can maintain the desired voltage profiles, compensate for voltage fluctuations, and stabilize the grid during voltage sags or swells. Load flow control. FACTS devices can help control the flow of power on transmission lines by adjusting line impedance. This allows for efficient utilization of existing infrastructure and helps prevent overloads, reducing the need for costly line upgrades. Power oscillation damping. FACTS controllers, particularly thyristor-controlled series capacitors, TCSCs, and thyristor-controlled braking resistors, TCBRs, can dampen power oscillations caused by various factors such as generator imbalances or sudden load changes. This improves the stability and transient response of the power grid. Congestion management. By controlling the power flow on congested transmission lines, FACTS controllers can alleviate congestion in the grid. This helps in preventing bottlenecks, reducing power curtailments, and maintaining grid reliability. Contingency management. FACTS controllers enable rapid adjustments in power flow during contingencies, such as line outages or sudden load changes. This ensures that the system remains stable and continues to deliver power without disruptions. Reactive power compensation. FACTS controllers can provide reactive power support to the grid, improving power factor and reducing the overall demand for reactive power generation from power plants. This leads to better utilization of generating resources. Wind and solar integration. As renewable energy sources like wind and solar become more prevalent, FACTS controllers can aid in integrating these intermittent resources into the grid. They help manage the fluctuating power outputs and maintain grid stability. Long-distance power transmission. FACTS controllers can enhance the transmission capacity of long-distance power lines by regulating voltage levels and managing power flow. This is particularly important for transmitting power from remote generation sources to load centers. Harmonic mitigation. Some FACTS controllers can suppress harmonics and mitigate harmonic distortion in the grid. This improves power quality and reduces the risk of equipment damage due to harmonic resonance.
There are several power quality issues that can affect electrical systems. Voltage fluctuations. Voltage sags, dips, brief reductions in voltage, often caused by starting large loads or faults in the power grid. Voltage surges, spikes, short duration increases in voltage, usually caused by lightning strikes or switching operations. Voltage imbalance. When voltages in a three-phase system are not equal, it can lead to uneven distribution of power among phases and cause overheating in motors and other equipment. Frequency variations. Deviations from the standard frequency, e.g., 50 or 60 Hz, can impact the operation of time-sensitive equipment like clocks and motors. Harmonics. Harmonics are non-sinusoidal waveforms that are integer multiples of the fundamental frequency. They result from nonlinear loads, e.g., electronic devices, and can cause overheating, equipment malfunction, and interference with communication systems. Voltage flicker. Rapid and repetitive changes in voltage can cause flickering lights and disrupt the performance of sensitive equipment. Voltage unbalance. Unequal voltages in a three-phase system can lead to uneven load sharing and reduced efficiency in motors. Power factor issues. A low power factor results from reactive power consumption in a system. It can lead to increased energy costs and reduced system capacity. Transient voltage. Short duration, high energy voltage spikes caused by lightning strikes or switching events can damage equipment and disrupt operations. Voltage swells. Short duration increases in voltage that exceed the normal range, often caused by sudden load reduction. Electromagnetic interference, EMI, and radio frequency interference, RFI. High-frequency electrical noise generated by various sources can interfere with the proper functioning of sensitive electronic devices. Interruptions. Complete loss of power for a short or extended period can disrupt operations and damage equipment, especially if proper backup systems are not in place. Voltage regulation. Consistent and stable voltage levels are essential for the proper operation of electrical equipment. Poor voltage regulation can lead to underperformance or damage to equipment. Resonance. Resonance occurs when the natural frequency of a system matches the frequency of harmonic currents, leading to excessive. Proper design, maintenance, power conditioning equipment leads to its improvement. Common types of power quality mitigation equipment. Voltage regulators, stabilizers. These devices help maintain a steady voltage output by compensating for voltage fluctuations, ensuring that connected equipment receives a consistent voltage level. Uninterruptible power supplies, UPS systems provide backup power during outages, ensuring continuous power supply to critical equipment and preventing voltage disruptions. Surge protectors. Surge protectors, or surge suppressors, are used to limit the voltage spikes caused by lightning or sudden voltage changes, safeguarding sensitive equipment. Voltage sag and swell mitigation devices. These devices detect voltage sags, temporary drops, and swells, temporary increases, and provide compensating voltage adjustments to minimize the impact on connected equipment. Harmonic filters. Harmonic filters reduce unwanted harmonic distortion in the power supply caused by nonlinear loads like variable speed drives, thereby improving power quality and preventing interference with other equipment. Active power filters. These filters dynamically monitor the electrical network for harmonic distortion and actively inject counteracting currents to cancel out the harmonics, ensuring cleaner power supply. Power factor correction equipment. Power factor correction devices optimize the power factor of electrical systems, reducing reactive power demand and improving overall system efficiency. Isolation transformers. Isolation transformers provide electrical isolation between the input and output, protecting sensitive equipment from voltage spikes and ground loops. Dynamic voltage restorers, DVRs. DVRs automatically inject the necessary voltage to counteract voltage sags and maintain a stable voltage level during transient events. Active voltage conditioners, AVCs, similar to DVRs. AVCs correct voltage sags, swells, and interruptions to provide a continuous and stable output voltage. Static VAR compensators, SVCs. SVCs are used to regulate the reactive power in an electrical system, helping to maintain voltage stability and power factor. Energy storage systems. Batteries and other energy storage devices can be used to store excess energy during times of low demand and release it during peak demand, improving power quality by reducing voltage fluctuations. The selection of appropriate power quality mitigation equipment depends on the specific power quality issues present in a given electrical system. A distribution voltage regulator, DVR, is a device used in electrical power distribution systems to manage and regulate voltage levels within a distribution network. DVRs are typically installed on distribution lines and are responsible for maintaining a consistent voltage level as electricity is delivered from substations to residential, commercial, and industrial customers. Here's how they work. Voltage sensing. DVRs continuously monitor the voltage levels at specific points within the distribution network. Control logic. Based on the voltage measurements, the control system of the DVR determines whether voltage regulation is required. If the voltage is too high or too low, the DVR takes corrective action. Voltage adjustment. The DVR employs various techniques to adjust the voltage. These techniques might include tap-changing transformers, voltage boosters, and other voltage control mechanisms. Feedback loop. The DVR's control system operates in a closed-loop fashion, meaning it continually adjusts the voltage output based on the measurements it receives. This helps maintain a stable and optimal voltage level. Remote monitoring and control. Many modern DVRs are equipped with communication capabilities that allow operators to monitor their status and performance remotely. This is particularly useful for utilities to efficiently manage their distribution networks. Benefits of distribution voltage regulators include improved voltage quality. DVRs ensure that the voltage supplied to consumers remains within specified limits, preventing equipment damage and maintaining efficient operation of electrical devices. Energy savings. By maintaining voltage levels within an optimal range, DVRs can help reduce energy losses in the distribution system. Voltage stability. DVRs contribute to the stability of the overall electrical grid by regulating voltage fluctuations caused by varying loads and changing network conditions. Enhanced reliability. Voltage regulation contributes to the overall reliability of the electrical distribution system by preventing equipment failures due to voltage-related issues. Reduced voltage flicker. Voltage flicker, which can cause lighting fluctuations, is mitigated through the use of DVRs. Distribution voltage regulators play a crucial role in maintaining a well-functioning electrical distribution system, ensuring that end users receive reliable and high-quality power without voltage-related disruptions or damage.